All right, hello everybody. I just want to make a short video today, kind of on the heels of the supposedly short video I just made about covariance and correlation for you all. But today what we're going to do is look at some basic R commands for interpreting and basically using the concepts of covariance and correlation in R in a way that will make our life simpler, but also in a way that will be very explicit so you understand what's going on in R when we use those commands. I've got the commands up here. I haven't made one of these videos for a while, so it's in the R commands tab on the course webpage, and it's down here on the bottom of that page for now, October 22nd, which was yesterday actually. But if you click on that, it'll pop open. And I've got a couple of commands here at the top, which I'm not going to run through, but they will show you how to export a data frame to a file outside of R, which is a question I've gotten about before in this class. And it's basically the write.table command. And then the only issue there is how to specify the path and file directory for wherever you might want to put it. I'm not going to use that today just because I want to keep things relatively focused and simple, but these are the commands if you should ever want to do that sort of thing. If you've created your own data frame in R and want to save it for later. Let's check out how correlation analysis works in R by first loading up a different data frame which we haven't created and which was in fact created by an academic named Harold Bayan, who works up at the University of Alberta, or at least he did when I got this. I think he's still there, but I can't be sure. But anyways, this is a very nice data set. Well, first of all, I've called it mono words here. And I'll show you what it looks like in a second. Just by putting this link up here in the Firefox browser I've got open. So I've loaded this all into a data frame called monowords, and I've attached the data labels inside of R, my console. But what you see here is a lot of data. And I kind of want to walk through each field and each line, what they means. But there's 4,568 all together. And these are all the monomorphemic, monosyllabic nouns and verbs in English. So we're starting out with doe, horse, dress, pork, plug, prop, dawn, dog. I don't know why they're in this order, but they are. And you can see, yeah, they're all one syllable and they don't have any additional morphemes in them either. What these different columns or fields mean for each data line is there is, first of all, RT lex decision. That's the log of the reaction time to a lexical decision task for the word. And right next to it is the log of the reaction time to a naming task for the word. That's RT naming. So I'm kind of starting out with complicated stuff here. Actually, even before we get into what these two things mean, I'll say there is another column here for observation. And that actually just goes through gives a specific number or a unique number for each row in the data frame. I used to organize my data files like that. I don't do it anymore, but if you do, one thing you can do when you load that data into your R console is that in addition to this part of the command, which specifies that this first row is just a header of variable names, then you also can use this command, which says row.names equals 1, which means that these are just unique identifiers for each row of data in your data frame. So nothing really important is going on there. In fact, if we do look at the summary here for monowords, there's no observation variable in monowords. It's just saying, okay, these are unique identifiers. So I don't organize my data like that anymore because I feel like it's kind of gratuitous or perhaps a waste of space. But it is in here, even though we have over 4,500 data points or words in this data set. So anyways, what do I mean by lexical decision task for a word or naming task for a word? So basically, if you present words like these to a participant in an experiment and say, is that a word or not? And you can measure how long it takes them to decide that it's a word. So like the word plum, they'd see that on the screen in front of them, and then they press a button to say, yes, that's a word. Then like in a different trial, they might see the word plub, and then they have to say, no, that's not a word, right? So they're seeing words, they're seeing non-words. They have to decide is what they're seeing a word or not a word as fast as they can. So this is a measure of the amount of time it takes them to do that. And when I say log, that just means we're taking the logarithm of that reaction time. And if you don't remember what logarithms mean, don't worry about it because it's not going to matter for now. In fact, I don't even know if we're going to have that matter for the rest of the way. But either way, that's what they do. And the reason they do that is just to kind of simplify the representation of the amount of variation in the reaction time there, reduce it kind of on terms of the scale they use. But again, don't worry about it. It's just a number, and bigger numbers mean longer time, and shorter or smaller numbers mean a shorter amount of time. So this would be like a shorter amount of time. The word skirt, let's see, the one right above it has a longer amount of time. So that's arc, ARC, so on and so forth. They also have reaction times for naming. And so naming is when you see a word like dog, and then you are expected to say that word. So like a word like dog, you can say pretty quickly, it's short, and it's really familiar, right? So it's easy to read out loud. That's basically what you're doing, is reading it out loud. A word that maybe takes longer to say out loud would be this one, which is hooch, which is a little bit longer and maybe not as familiar. So that's what that means, that RT naming. And in case you're curious about a measure of like familiarity, there's one right there. So I'll contrast those two. So there's measures of familiarity and frequency in this database. Here are the frequency. Here's the frequency measure, and here's the familiarity measure. So I think if I go back to my guide, so I don't have the scale, but I think familiarity is probably ranked on a scale of 1 to 7, based on how much the numbers we see here. So like a really familiar word is R, which has a ranking of 6.73. So we see this one a lot, right? So it's close to the limit. A word that's not so familiar is whirl, like I guess a whirl in your hair or something like that. So that's down at the low end. That's like 1.44. But this is a subjective measure. So you just say, oh, here's the word dough. How familiar are you with this word? And on our scale of 1 to 7, subjects will just rate, 1 through 7. So you can do that, collect that subjective rating. You can also collect a more objective rating of how common a word is by counting the frequency from some data set or corpus, I guess you could say. So collect a huge amount of, writings or publications from somewhere. Like I think they've made a count of like all the words used in the Wall Street Journal over many, many years. And that's a lot of output for a newspaper that gets published every weekday, because those businessmen who read the Wall Street Journal need their breaks on the weekend. You can just simply count the number of times you see a word in a data corpus like that. So like you see R a lot, right? And that in that particular case is going to correspond to a high familiarity rating, but they're not always exactly the same, right? So maybe sometimes you'll get a word that's really frequent, but not that familiar. I'm just trying to look for one here that might be a bit of a disconnect. So hooch is low on both the frequency and the familiarity scale. The word grouch is less frequent maybe than it is familiar, that sort of thing. Okay, so anyways, without much further ado, there's also count of the letters in each word. Oh, and then neighbors, right? So this is kind of important. This is more important, I guess, for just understanding how people process words than it is for statistical purposes per se. But hey, this is a statistics class for linguists, so this is what we're going to learn. So the neighbors, there's two measures of neighbors, or how many neighbors a word has in its neighborhood. What that means, usually I ask people in the class what it means, but a neighbor of a word is, say, a word where if you just change one phoneme in it, either through addition, subtraction, or modification, I guess, then if you're able to create a new word by doing that, then that word has a neighbor. It's, in that case, a phonological neighbor, if you're just adding, subtracting, or modifying a phoneme in it. It's an orthographic neighbor if you're adding, subtracting, or modifying some written letter in the word itself. And just looking at these, I can't come up with a lot of neighbors off the top of my head. So greed, here's one. Greed has a neighbor of green, right? Where you just change the D to an N. So those are two similar words, both orthographically and phonologically. And I don't know how many neighbors greed has in general. This, I guess, is a count of 16 and 24, respectively, for orthographic and phonological. A word like hooch apparently has no neighbors, even though I could think of like hoot. So I'm not actually sure how they counted that. But anyways, that's the idea. And usually when it's interesting, so if a word is more frequent or more familiar, you can usually process it more quickly in terms of processing measures like naming or lexical decision. But if a word has more neighbors, then it takes you longer to process it in these sorts of tasks usually. So there's kind of a trade-off often. Well, I mean, they're independent measures, familiarity or frequency on the one hand, and then neighborhood measures on the other hand. They can vary independently. Sometimes they coincide, sometimes they don't, which, might make for a good sort of analysis for things like covariance, like how often are these things covariating with each other, or how well do they correlate with each other. So after all of that, there's also a measure of correct lexical decision, which is the number of listeners who correctly identify the word as a word. I'm not going to say anything more about that. Let's just dig into the data a little bit to see how we can play around with it. Okay, so let's check out what sort of relationship there is between the familiarity and the frequency of a word. Yeah, and so apparently there's a backstory about this too. The frequency we have in this database is from the Celex database. And I can't remember where Celex gets all of their counts from, but it's from somewhere, from some published material, wherever. And Celex existed, in the 90s, so it's probably based on mostly pre-internet sources. But people can work long and hard to create these frequency databases with the hopes of trying to figure out on the basis of that information like how people might do in a task like lexical decision or naming or what have you. But it's funny because when people first got the idea that, maybe we can just ask people, we can ask the participants in our studies, like, well, how familiar are you with a word like hooch? And it turns out often the familiarity measures can do a better job of like predicting how that person will do on a certain word processing task than the frequency measures, which are more objective, because everybody's experience is unique to themselves, right? So some people are more familiar with certain words and some people are more familiar with others, depending on just what you've experienced in life and what you happen to know. Let's try to figure out how those two measures correlate with one another, though, because generally I think we'd expect more frequent words to be more familiar to more people, right? So let's say we're going to take a look at the familiarity measure out of this database, which I've called monowords in my R console. And I'm just going to pump out here the number of words, or actually this is going to be a subset of rows where these are just all the words where the familiarity is above average. What's that stupid joke? I grew up in central Minnesota, and there was a famous radio show that was made there. If you can believe there was a famous radio show in the late 20th century, there was, by a guy named Garrison Keillor, who described the residents of some fictional Minnesota town as the men. The women are all strong, the men are all beautiful, and all the children are above average. That was a long way to go for a dumb joke, but in this case, all of the words in this selection will be above average in familiarity. And since there's many of them, since there's about 2,000, it's hard to see them all at once. But like R is above average in familiarity, and chunk, believe it or not, or face is above average in familiarity, so on and so forth. That's how you find that out, just with a simple R command. But you can count the number of rows if you don't want to have to look at them all this way, just with this nrow command. So like I said, I think it's 4,568 total words in this database. About 2,154, not quite half, are going to be more familiar than average, which means the opposite is true for the words that are less than average familiarity. But what I want to do is replicate that contingency table sort of example that was given in Keith's textbook. And so that was looking at sort of format measures for different vowels, but I want to do this for familiarity and frequency measures because, well, I kind of stumbled across the description. I stumbled through the description of it when I was talking in the lecture, and maybe we can make it a little more clear if we make it explicit here with actual examples. So let's look at how many words there are that are above average in familiarity and at the same time are above average in frequency in this data set. So this tells me I have 1,664. And I know I try to avoid using Excel in this class, but I'm going to use it here just to kind of like keep this data in one set or one place where you can see it. Yeah, so let me just do this. Yeah, and I'm going to make this bigger as well. So we've got frequency on this dimension, and then we're going to say above average and below average there. And then for familiarity, we're going to have it over here. And I can't do the same trick with that, but we'll just put it in bold and pretend that that makes it better. Yeah, so above average for both is 1,664. Yeah, again, normally I do this on the board in class, but whatever. You got to make do in pandemic life. All right, so how many words are above average in familiarity and below average in frequency? We've got 490, so we'll put that in this corner over here. Maybe we can center all this stuff to make it look slightly nicer. Take advantage of some of the functions of using software to do this for us. How about how many words are below average in familiarity and above average in frequency? We've got 458. And then how many are below in both dimensions? We've got 1956. So this is maybe a more relevant or clear example of this sort of correlation that we're seeing between two different variables. So it's not exact, and we know exactly where the data is coming from here. But normally, if a word is above average in frequency, that objective count, it's going to be above average in that subjective sense of familiarity as well. If a word is below average in frequency, normally it's going to be below average in familiarity, but we do get these two across the other diagonal here that are kind of mismatching with each other. So there's a relationship, but it's not absolute, right? That's the whole point of that sort of contingency table. I've got this, I also pointed out, got a question here for familiarity in letters, which is the number of letters literally in the word. So like dough has 3 letters. We could try the same thing with that. Let's see what it gives us. Put the table down here just to make space. This will be letters. Oop. All right, so I'm not going to save it. I compulsively save things. All right, because I don't want to lose my work, as I'm sure you guys know from working with computers yourself. All right, anyways, we're just going to change this variable. For how many of these are above average in both? The number is 818. So the letters are also already looking a little bit different than what we got before. How many are above average in familiarity, below average in the number of letters? It's 1336, so it's working out differently already. Let's go below familiarity, above average letters, 1048. And then below for both, and we get 1366. So that's kind of interesting for a number of reasons. So we don't get this sort of apparent linear relationship or this diagonal boosting up the numbers anymore. Instead, we get, well, a lot of numbers over here. More than half of these words have below average number of letters, which is kind of interesting. So the above average letters are counting for more. They're pushing the mean kind of in a skewed direction there. And we don't get this sort of connection between above and below that we saw before. This one and this one are not consistently bigger than the other two, right? So whatever relationship there is, that it's not a clear correlation. But up here we do have a seeming correlation that's just not absolute. Okay, so we can also look at that in a couple of different ways just by plotting the data. And if you've ever wondered how to make a scatter plot in R, here's how you do it. It is simple. You just say plot and put this value for the x dimension or the horizontal dimension, and then this variable for the y dimension or the vertical dimension. And I'll move this around here so you can see both labels. But yeah, this is how familiarity kind of lines up with frequency. And we see what sort of looks like a line, right, with, it's made up of a bunch of dots and it's kind of messy. It's not perfectly straight or anything, but it's obviously there's a trend, right, from the lower left-hand corner to the upper right. Yeah, so it looks like a linear relationship. It's just not, like I said before, absolute. We can try the same thing with the letters, and unfortunately it's going to look a little different because letters is not a gradient measure. So letters is just whatever, I guess you'd say. It is a gradient measure, but it's more granular than the measure of familiarity, which has lots of numbers after the decimal points in it. So we get these lines where these are all the words with 3 letters. These are all the words with 4 letters. Anyways, what you don't see in any clear way is some sort of correlation here between the two. And in fact, it's not even easy to really interpret what's going on here altogether. Should probably find out what these two-letter words are. But I don't have time. Anyways, there's a lot more information in those plots than we're getting out of the contingency table is kind of the moral of this story. So this gives us a general sense of what's going on. But if we look at this in graphical form, and it's always good to look at things in graphical form, we see that, there's a lot more information here than just putting things in 4 boxes. So there's value in trying to dig out that information. How can we connect or quantify all that connectedness between the little dots? And we're going to start by using the concept of covariance. And to give you the specifics on how this works, we'll look at the first 5 words in this data set. And again, I don't know why Harold Bayan started with these 5 words, but this is the way it works out. So we got dough, whore, stress, pork, and plug. Okay. And I've got little commands here about checking out the values of these first 3 variables. Actually, maybe I'll make this explicit. We can see them just by plotting out these 5 words in this table like this. But if you want to just focus on these variable values, this is what you get for familiarity. And then this is what you would get for frequency. And what we want to try to find out just with this tiny little data set is like what sort of connection is there between these variables. So between familiarity and frequency there, between familiarity and frequency there, so on and so forth. And we can also look at letters, just because we kind of suspect that there's not going to be any super meaningful connection between familiarity and letters, right? Knowing what we know now. Right, just looking at those variables, covariance is based on how much each measure of a sample differs from that sample's mean. So I want to calculate that difference for these values with each observation in the familiarity and frequency samples. But this is kind of a crucial part of this, which I'll repeat because it winds up being important as we go through this. But we're looking at how much each measure of a sample differs from that sample's mean. And that's how we can get a sense of whether 2 different variables will vary in the same way, whether you get that same sort of difference across the board for its values. So what we're going to do is calculate those differences for each of these 2 first little data sets. So first for familiarity, and then secondly for frequency. We'll call them fam diffs and frequency diffs, or frec diffs, I guess. There's a nice non-word frec. Frec diffs is another nice good non-word. Anyways, these are the differences between the individual values and the mean values of these measures. So I don't know exactly what the mean familiarity value would be. I guess it's going to be 4.04 because this is 4.43 and that's 0.39 more than the mean. So for the third word, we have a lot of familiarity because this is a highly positive value. And for the first word, we have not much familiarity because this is a very negative value. So the first word is dough. That's our low in familiarity. But we're kind of normalizing it a bit just by subtracting all these measures from the mean. So the normalized version of this is negative 1.67. And stress is a highly familiar word, apparently. I don't know if they surveyed college students for this or what, but this is a familiarity of 5.6. And we can kind of compare what's going on with those in frequency. So again, we see the same sort of thing for the frequency differences. Maybe I'll make this bigger so we don't have to go back and forth. But for familiarity, for frequency, dough is not very frequent and stress is very frequent. But where do we get mismatches here? So those wind up being interesting too. So mostly let's focus on where we get mismatches in sign rather than magnitude. But the second word, hor, is familiar. It's on the positive side of familiarity, but it's on the negative side of frequency. So that kind of suggests that you might hear this word more often in real life than you see it in print, perhaps. And then we can kind of look at a slightly opposite case for pork, where it's on the low side of familiarity and it's on the slightly high side of frequency over here. So maybe this word appears a little bit more in print than it does in your real life. Because maybe this is the Wall Street Journal database and people are talking about pork bellies or something like that. I don't know. That's another Midwest joke. I'll just let it go. Anyways, we've already taken a look at these specific difference values. What I want to do next is take the product of those two sets of differences. So I'll do that first. And then, I'll show you where it comes from. So if you remember, here, first of all, here's our contingency table for the formant frequencies from the lecture. And then secondly, what I'm doing here is I'm getting this product of deviations, or basically this part. I'm looking at the deviations from the mean of each variable and then multiplying them together. So it's basically this part right here. And then eventually I'm going to want to sum them all up over all 5 observations to get that sum of the product of deviations. But to begin with, I get these numbers, right? So just looking at some of the examples we started with. So this word dough is low in both familiarity and frequency. So when I multiply those together, I get a large positive number. And this word stress was on the high side of both measures. And when I multiply those two values together, I get another large positive number. These are just kind of in the middle, not doing much. But the interesting part is the sign change. So for this word, second word, hor, it was on the opposite side of the two measures. So when I multiply that together, I get sort of a low, it's a negative number to begin with, and it's the lowest negative number, I guess you would say, in this particular little set. So when I add these all up, dough and stress are going to contribute highly to the sum, and a word like hor will take away from that sum a little bit. So these will make it look like things are highly correlated, and this one will make it look like things are not well correlated. Okay, so let's sum them up like this. And this number is really not going to mean a whole lot. It's just a number of making these calculations for these 5 data points. And we get something close to 4 for that. The last step here is that to actually calculate covariance, we want to take that sum. So we now have the sum of the product of deviations. What I want to do next is divide that by the degrees of freedom to get covariance. And I have this question in the commands here. It's like, what is the degrees of freedom? It's n-1, which should hopefully be familiar by now because we do have to calculate the mean here. So we're taking away 1 degree of freedom out of 5. So we'll divide this whole thing by 4 to get a measure of covariance, which is almost exactly 1. That's how you get that measure. And again, it doesn't mean anything really by itself, but here I'll show you how to do it the easy way, now that we've walked through all the painstaking details. You just put both variables that you care about within this cov command, and then you get the exact same number. It's almost exactly 1. Right, we can also look at a plot of these guys just to kind of get a sense of how much of a linear relationship there is between the two variables for only these first 5 data points. It looks like this. So I think we've got, this is stress over here, and this is dough over here, and then there are the other 3 words here in the middle. So we can kind of see that linearity going through. But this is a very small sample, right? So it's only 5. So it's not clear if this really is a relationship or not, but it's giving us a sense that it might be. And there's some messiness here in the middle. Right, so, but we can actually quantify how much messiness there is by taking a look at the correlation coefficient between the 2 samples, which is this, and it's 0.8925, so on and so forth, which is pretty good. So if you remember, our will range from, that correlation coefficient measure will range from -1 on the low end to 1 on the high end. In this case, we're at 0.892, so we're pretty close to 1. This is pretty close to a perfect correlation. And we can still see the messiness in there, but that's what that looks like, basically. Right. And I did calculate the correlation the easy way here. We can calculate it the hard way here by just dividing the covariance by the standard deviations of the two variables. It's going to get us to the same spot, but this is sort of where this is coming from, basically, for now. That's how we get that number. And I'm not going to walk through any more details than that. I will stop for now. I will leave you with a bit of a cliffhanger, though. I'm going to show you this game. It's called Guess the Correlation. And to not spoil it, because I'm putting this at the end of a video that you might not watch. I don't know. Don't want to throw any accusations out there. But it's at the end of a commands video, so who knows what you're doing. Anyways, this is a game called Guess the Correlation. So I'm going to play it again at the beginning of the next lecture. But this is a fun little game which just shows you a plot that kind of looks like this. And then you have to guess what the R value is for this guy. So we know this is 0.89. It looks pretty linear. This is maybe less linear. I don't know. Let's say it's 0.7. Whoa, it's 0.83. So this is the true R, so on and so forth. I'm going to play this again at the beginning of the next lecture because it's kind of fun. And usually I have people play it in class just to see how well they do. But that's what we're thinking about now is correlation in terms of R. We're trying to quantify the connection between these two variables, which are both gradient. I'm going to stop there because it's long enough already, and I'll pick back up again in a couple days with further adventures in correlation and linear regression. So see you then.